Hey Wiley, how are you?
Hello. Oh, good.
That's good, that's
Oh,
good.
a little tired today.
Tired?
Yeah, I had two 80-minute lectures back to back
Two 80-minute lectures back to back. Oh my God.
in like the morning. Yeah.
The morning time.
Yeah, and I just took a nap like right after.
Same. I took a nap right after I went home from school too. Like that's how much
Yeah.
for
I don't know
sure.
why I'm so tired.
Yeah.
Oh,
Um, what classes are you taking again this quarter?
uh, I take OChem,
Mm-hmm.
taking Biz 2B, uh, Latin 2,
Mm-hmm.
and like a geology lab, like lab
Mm.
class.
Right. And what were the two back-to-back classes you had today?
Oh, I have another class. It's just for like my major.
Uh-huh.
It's like learning about California environmental law. And then the other one was the like a paleobiology lecture.
Geology
Yeah.
lecture. I see. I see.
Yeah.
That's interesting. Um,
Apparently, oh,
What days are your OChem classes?
oh,
Like
it's just Monday, Wednesday, Friday.
Monday, Wednesday,
The
Friday. I see.
50-minute.
Uh-huh. Okay. Let's see. So you only had one lecture so far. The next lecture is tomorrow. Um,
Yeah.
let's go over the alcohol like redox
Yeah.
reactions, organometallic Grignard reactions, stuff like that. Let me share my screen. Let's see.
Just write this down. Oh,
Okay. So in Gen Chem, what do you remember about the definitions of oxidation and reduction?
oh, Gen Chem?
Hmm.
Like in terms of electrons or like adding
Yeah,
elements?
like anything you know about
Oh,
oxidation.
okay. I'm gonna just pull this from Biz 2A, like
Uh-huh.
last quarter. When it's reduction, you add hydrogens.
Mm-hmm.
And
Yep,
there's
yep,
or you lose oxygens, and it's like vice versa for oxidation.
yep. Um, Reduction is adding hydrogens or lose
Yeah, lose
electronegative atoms like oxygen, right? Because later you're gonna see you can reduce things where you're not removing oxygen, but you're removing nitrogen, right? But the most
oh, okay.
common atom is oxidation, where when you reduce something, we typically lose oxygen, but in general, it's an electronegative atom. Like it could be nitrogen as well,
Yeah.
right? Because when you reduce nitrile, you're not losing oxygens, you're losing nitrogen bonds to nitrogen. Um, Oxidation is the vice versa, opposite of it. We are going to lose hydrogens and add bonds to electronegative atoms like oxygen. So this is like typically what we use for OChem. GenChem, it's like oil rig or Leo the Lions Gur, where oxidation is like the loss of electrons and reduction is the gain of electrons. But we'll think about it more in terms of hydrogens and electronegative atoms, right?
Yeah.
So I'm going to make a chart here where we are going to show the most oxidized organic compound um, to the least oxidized organic compound, or vice versa, like the most reduced organic compound versus the least reduced organic compound.
Uh-huh.
So we're going to start with methane, which is CH4 right here, where this carbon here, because it has four bonds to hydrogen, this is the most reduced organic
Yeah.
compound, right? And on the other end of the spectrum, we can have carbon dioxide, where this is the most oxidized organic compound because it has four bonds to oxygen,
Hmm.
right? So now we're gonna put the organic compounds in between, and I'm gonna go this way. I'm gonna reduce this carbon dioxide and go all the way to the methane. So one below that is going to be a
Carbonyl? Oh,
Yep,
or
carbonyl, but more
carboxylic
specifically a carboxylic acid. That's right. Um, and then one below that is going to be
aldehyde.
aldehyde. That's right. And one below that is going to be
Uh, alcohol?
yep, alcohol. That's
Oh,
right. Okay. Right. So if you think of it in terms of oxidation state, it's going to increase from left to right. Oxidation state. If you think of it in terms of reduction state, it's going to increase from right to left.
mhm.
Okay. Now we're going to focus on these three mainly for now for when we first learn about oxidation reduction reactions in OChem,
Yeah, okay.
which are the alcohols, aldehydes, and carboxylic acids. There's going to be three different types of alcohols. There's going to be primary alcohol, secondary alcohol, and tertiary alcohol. Um, where a primary alcohol is going to look like this, secondary alcohol is going to look like this, and then a tertiary alcohol is going to look like this, right? The reason why they are named the way they are is because if you look at the carbon directly attached to the oxygen, that carbon is attached to one other carbon, making it a primary alcohol, right? If we
Yeah.
look at the secondary alcohol, that carbon directly attached to the oxygen is attached to two other carbons, secondary alcohol.
Mhm.
Tertiary, three other carbons, tertiary alcohol, like that. Okay, so we're going to look at the oxidation reactions first,
Mhm.
but before we could do that, we're going to think about oxidizing agents. And these are reagents that are going to oxidize a molecule, right? So think of them as agents doing an action. And these oxidizing agents here are going to oxidize a molecule. There's going to be two types of oxidizing agents that you're going to see most likely. There's a weak one and a strong one. The weak oxidizing agent is going to be PCC. You could see CH2CO2, but that is the a product solvent, right?
Oh, okay.
Um,
PCC, CHCl2.
mhm. CH2CO2. For the strong oxidizing agent, you could see this abbreviated as Jones or Jones reagent. And there's like different types of forms you could see this in. You could see this in the form of H2SO4 or H2 CR. Well, actually, and a
Oh,
let's see. Oh, wait. Oh,
okay.
hey Nandini. So
Hello.
I'm going over redox reactions with Wiley right now. But after
Okay.
I go over oxidation, we could work through one problem of yours, and then we alternate back and forth.
All right. Cool. Thanks.
Yeah. So there's different forms of Jones reagents that you can see, which is Na2Cr2O7, H2SO4, water. There's Na. Oh no. There's CrO3, H2SO4, water. You could also see H2CrO4 and just water. But the most important indicator here is if you see chromium and a lot of oxygens, right? Chromium and a lot of oxygens. That is a big indicator of a strong oxidizing agent, right? Because oxidizing agents is going to oxidize something. We're going to add oxygens to a molecule. So when you see chromium and a lot of oxygens, that's a big indicator of a strong oxidizing agent, right?
Mhm.
So I'm going to show you this like this, where we're going to look at primary alcohol, secondary alcohol, and a tertiary alcohol using these reagents.
Okay.
If we use a primary alcohol, and we react it with PCC or Jones, because PCC is a weaker oxidizing agent, we are only going to oxidize that alcohol into the aldehyde, right? Where if you specifically focus on this carbon here that I'm highlighting in blue, this carbon right here has 1 bond to oxygen and 2 bonds to hydrogen. But when we oxidize that, we are removing 1 bond to hydrogen and we're adding another bond to oxygen like that. Right?
Okay.
And we're removing 1 bond to hydrogen like that. So what would you expect this primary alcohol will convert into if we use a stronger oxidizing agent like Jones?
Would it be carboxylic
Yep, carboxylic acid.
acid?
Right, because we remove both of the hydrogens and we add 2 bonds to oxygen in exchange for that, right? Because now this carbon here in blue has 3 bonds to oxygen like that. Right?
Okay. Do
So
we have to know the mech for this, or is just we just know it just changes to these products?
yeah, do not need to worry about the mechanism for this. Just
Okay.
need to know what it does, like for
Okay.
purposes and synthesis purposes. Right. For secondary alcohol, it will not matter what you use, PCC or Jones, you're gonna get the same thing, right? Where we see that that blue carbon here holding this alcohol only has 1 hydrogen, so we only have 1 hydrogen to remove in exchange for 1 bond to oxygen, giving us a ketone. So whenever you oxidize a secondary alcohol using PCC or Jones, you will always end up with a ketone. Right? Now, if we look at the tertiary alcohol, this carbon here in blue holding the alcohol has no bonds to hydrogen at all. So because it has no bonds to hydrogen, when we try to oxidize it using PCC or Jones, this would be no reaction.
Okay.
Right. Another thing that you might see is that if you have an aldehyde as a reactant instead of an alcohol, you can convert that aldehyde into a carboxylic acid by using the strong oxidizing agent Jones. Right? You cannot use PCC here because PCC is not strong enough to convert or oxidize that aldehyde into the carboxylic acid. You would need to use a strong oxidizing agent like Jones to oxidize the aldehyde all the way to the carboxylic acid.
Okay.
Okay, so I'm gonna give you 2, 3, 4, 5 practice problems here, and I want you to predict the product or predict the reactant, depending on if I give you
Oh, okay. Okay.
the product or the reactant. Okay.
Yeah. Can you zoom out?
Yeah. Hmm.
Like, are those all 5 problems? Okay. I'll just
Yeah.
gonna try.
Yeah. These are all the ones. Right.
Okay. All 7.
Uh-huh. Okay, let me change the last one really quick. Let me change the last one.
Oh, okay.
Change the last one. Okay. These are all the ones now.
All right.
Oh yeah, Nandini, I looked at the practice exams that you sent me. I starred the ones that had the topics that you sent me. So we could work through those problems.
Okay, cool.
Uh-huh. What time is it over there for you right now?
12:20.
12:20? Oh my gosh. What time do you usually you go sleep?
Like 3 o'clock.
3 a.m.?
Yeah.
Dang, oh my gosh. Like you have late classes probably then, huh? Like your classes are in the afternoon or evening?
No, I'm on break right now until like January 27th, I think.
Oh, I see. Okay, yeah.
And my final is the 31st because I had to like reschedule to take it.
Right, yeah.
Like
I
my
was
sleeping
gonna say like
schedule is messed up.
yeah, because I also slept around like that time, like 3, 4 a.m. during break, but like during school time, I can't do that because I have class at 7:30 a.m. in the morning.
That's horrible. I would never do
Yeah.
it myself.
But what school do you go to?
I go to Stony Brook
Stony Brook in
in New York.
New York. New York. I see, New York.
Yeah. Are you a master's student or something?
Uh, a graduate student in chiropractic school right now. So I'm working to get my doctorate degree in chiropractic, DC degree.
That's really nice.
Uh-huh. What's your plan after college?
I'm pre-dental.
Oh, pre-dental. I have a friend that's also pre-dental.
Yeah.
He unfortunately didn't get in the first cycle, but he's applying against next cycle. So he's
Oh,
working as a dental assistant right now, volunteering and retaking his DAT soon. He's studying
oh,
for it again.
good luck to him. I hope he gets it.
Yeah. But this time he's applying to out-of-state schools because the schools in California I heard were competitive.
Yeah,
So
yeah, similarly in New York too. I
yeah,
think California, from what I've seen, like especially if you go on Reddit or like Doctor Network, like you'll fall into a loophole. You'll see people with like 4.0s getting rejected. It's kind of like I don't know. It's not sad, but it's like it's kind of sad because it's like a lot of people spend so much time on their application and they genuinely could be really good candidates and like they don't end up getting in.
right. I know, like especially all the experiences, like all their volunteer work, their dental experience, but the only thing that's limiting them is like the GPA. But some of those like grades you kind of don't need for dental school, like the classes that affected them. Right. What
Yeah,
year are you in college?
I'm a junior.
The junior, I see, I see.
I
When do
didn't
you plan on taking the DAT?
I next cycle, well, this upcoming cycle, I plan to apply. The only reason why I didn't take OCAM earlier is because I wanted to take it right before I took the DAT.
Uh-huh.
Like the content's kind of fresh,
Right.
so I'm taking it this year.
This year. Yeah, that's good. That's good.
Um, it's all right. It's cool.
Mm-hmm. There's OChem in there, I heard bio, math, and there's this perceptual section.
PhD,
I
yeah.
saw it. It's so weird.
It's like it's basically like our version of like what the car section on the MCAT, but not
MCAT.
really. Because like the
I know.
car section, I heard it's like pretty difficult because it's very conceptual,
Yeah.
and the PAT is like basically our version if you would try to compare the both. But
Right. Like you have to like it's very visual, like
yeah, but like that's a skill that is important, especially if you're planning
like
to go to dental school,
mhm.
what you're gonna be doing anyways.
Right, you gotta visualize the teeth and everything. Does the DAT test the anatomy of the teeth as well, or not yet? Like that's for dentals.
No,
I see,
not
I
at.
see.
I think
Okay.
I think for the bio section, because it's so like content heavy,
Mm-hmm.
it does go into like anatomy, but like I guess it's like very vague though. It's not
Mm-hmm.
like very, very, very what's the word? Like specific.
Mm.
Because I took a look into like the DAT booster stuff and like sorry, boot camp, and like their notes are very comprehensive, but I feel like it just depends on how good of a test taker you are and how like you're able to cram all that information in.
Right. Yeah.
That section is so content heavy. Like I know for a fact, like it's
Mm-hmm.
probably the lowest section for many people
Mm-hmm.
on their exams.
Yeah, it's tough. It's tough. It's like a 4 hour, 5 hour exam in total.
Yeah, that's without I think 4 hour without breaks and then like five with breaks, I think.
5 minute breaks. Yeah. Dang.
Horrible.
You see.
Oh, so I did this question
Uh-huh.
and I think I chose B was definitely one of the answer choices. And I
Mm-hmm.
think it was B and C. I think it was
Right.
choice.
Let me copy and paste this scenario down and ask you what products would we expect if we were to use, let's say, we have this alkyne and we could react it with sodium in ammonia liquid or H2 Lindlar's catalyst, aka poison catalyst. Are you familiar with these reactions? It's okay if you're not, just let me know. And
I Well, I know for a fact that we didn't really go much into depth on alkyne reactions. Like it
Mhm,
wasn't something that showed up on our exam. Like,
mhm,
but these are like the reductions like to turn into an
mhm.
alkene, right?
Great. These are the reductions that we turn it into the alkene. And there's going to be two types of alkenes that we can form depending on what reagent we use.
Oh, the cis and trans,
Yeah,
right?
the cis and trans alkene. That's right. Do you remember what reagent creates the trans alkene?
Uh, no, I don't remember.
Uh-huh. That would be the sodium ammonia liquid one. That one
Okay.
would create the trans alkene, and the H2 Lindlar's catalyst, that is the one that creates the cis alkene.
Okay.
Right. So when we use the sodium ammonia liquid, we're going to create this trans alkene. It's drawn kind of weird, um, but this is trans because if you draw a line through that alkene right there,
Hmm.
we see that this R group is on the opposite side of that R group right there. Right.
Okay.
But when we use H2 Lindlar's catalyst, we are going to have this alkene right here. Let me draw that alkene like that. Where when we make a line through that alkene, the argues are now on the same side or the same side of the line right here, making that a
Okay.
cis alkene. Okay, so now if we used sodium ammonia liquid, our A would be this trans alkene. If we use H2 Lindlar's catalyst, our A would be this cis product here.
Hmm.
Right. So they're asking for what B and C would look like. Are you familiar with the alkene reactions, like the different reagents and what reactions they do?
Um, kind of like with like OSO4 that
Uh-huh.
adds oxygen, an OH, right? To
Mm-hmm.
where the double bond is, and then Br2 adds like two bromines. I'm not sure if
Uh-huh.
it's cis or anti. I mean, syn or anti. I don't remember.
Mm-hmm. That's
Or
right. Because that is very important. Like the stereochemistry of these reactions, if it's going to be cis or anti, um, for Br2, that is going to be anti-addition. One
oh,
bromine is going to be anti to the other bromine, right? The OSO4, it will add two alcohols, one alcohol for each carbon of the alkene, right?
okay.
But that is going to be cis. So if I were to summarize those two reactions, like Br2, OSO4, and what they put, MO, and we were to do stereo selectivity, the Br2 reaction would be anti-addition, whereas the OSO4 reaction would be syn addition. And there's also regional selectivity of alkene reactions like Markovnikov or anti-Markovnikov addition, but we don't have to worry about that for these specific reactions because we're adding bromine or alcohol on both sides of the alkene. We're not adding it to the more subside of the alkene or the less subside of the alkene, so we don't have to worry about the regional selectivity for these reactions there, right? Okay. So now, based on that, let's now look at the products that we formed, the trans and cis alkene, and react it with either Br2 or OSO4. Right. So what would you predict the product would look like if we react this trans alkene with this Br2 here?
So there'd be like a Br added to like I guess the top face of the alkene and like the bottom face since it's anti, right?
Yeah, the top face or the bottom face. And more specifically, we could say one bromine is going to be wedge and the other bromine is going to be dash.
Oh, dash. Okay.
Right. And the top face, you could say is the wedge side. The back side, you could say is the dash side, like that. Right. Okay. What about if we used OSO4 instead?
They'd either both be wedged or dashed.
Right. Wedge or dashed alcohol. That's correct. You got it. Boom, boom, boom. OH. OH, like that. Okay. And this could have been dash as well, but I'm just gonna draw wedge right here. So now we're gonna determine the chirality of this entire molecule.
Okay.
Do you remember how to determine
assigning RNS?
A carbon is a chiral center? So you would assign RNS if there is a chiral center, right? So if there's a chiral center,
if it has I think four.
Yeah. Four different groups attached to it, right? So if we look at this carbon here specifically, that is a chiral center because it has a bromine, a benzene, this whole big bulky R group, and an invisible hydrogen right there. Right, so that's a chiral center. So I'm gonna star that here. This is also a chiral center right there, right? But even though a molecule has chiral centers, it does not mean that it is chiral, right? Because can you remember what factor would make it achiral, like the entire molecule achiral, even though it has chiral centers?
If it's meso?
Meso, right? Which has a plane of
symmetry.
Symmetry, yes, plane of symmetry. And in this case right here, we cannot clearly see the plane of symmetry. What we have to do is we have to rotate this sigma bond or single bond to show our plane of symmetry very clearly, right? This is the bond right here that I'm rotating. I'm keeping everything on the left side the same. And I'm just gonna flip the benzene and bromine around where the benzene is now gonna be down here. And the bromine is going to be up here. But when I do that, I'm inverting this dash bond right here that we see into a wedge bond.
Okay.
Like that. And because of that, we can now clearly see the plane of symmetry down that middle line right there. Everything on this side is the same thing as this side right there. Plane of symmetry. So because of that plane of symmetry, this is meso, aka achiral. Right. Now, would this molecule be considered meso or achiral?
Yes, if you rotate it. But no, it wouldn't, because then that would change the stereochemistry.
Yes, it wouldn't. Right.
but it does have a chiral center, does it not?
It does have a chiral center here and here, two chiral centers specifically. But when we do rotate it, like you said, it's going to flip the stereochemistry from a wedge to a dash. And those two chiral centers are still there. Nothing changes about those chiral centers. But we do not have a planar symmetry at all. So this entire molecule is considered chiral. It's not meso, but it's chiral.
Okay,
Right.
got
Whereas this molecule here is achiral because it has that planar symmetry, making it meso.
Okay.
Let me emphasize this plane of symmetry. Important. Plane of symmetry. Okay. Right. So now let's do the same, but for this cis alkene. Let me just do anti-addition. Wiley, is this like coming back from 128A last quarter for you? Like all these reactions?
Oh no, this looks like really familiar.
Yeah.
Yeah.
Right. So we said Br2 we add bromines on both sides of the alkene like this, and it's anti-addition. So one bromine would be wedge, another bromine would be dash. And this is good because we do not have to rotate anything. The benzenes are already like aligned for us to see like that potential planar symmetry, where we see that this molecule here has no planar symmetry, right? Because one bromine is facing up towards you, another bromine is facing down away from you, making that not a planar symmetry, not meso. Right?
Got it.
But if we react this with OSO4, we are adding alcohols on both carbons of the alkene, where it both could have been a wedge or a dash. And we do see a planar symmetry down there, making this meso and achiral. Right? All meso molecules are achiral, even though they have two chiral centers. Right? These molecules have two chiral centers. This one here has no planar symmetry, so this one here would be chiral. Okay, now this is all we need to answer the question. It was a lot. Like we, yeah, yeah. You had to like go through that rotation thing, to figure out this answer here. So if we used Na and liquid ammonia, B would be a racemic mixture. Let's see. If we used this, they're saying B, that's the one with Br2, racemic mixture, this one. Yes. So that one is false because this is achiral, so we cannot have enantiomers. Do you remember the definition of enantiomers? Like what would make two molecules enantiomers of each other?
If like the configuration of like a molecule was RR and then the enantiomer would be SS, right?
Yep, that's right. Every single configuration would flip. Like if that was RR, everything would flip to like SS. If it was RS, then it would flip to
Diastereomer.
yeah, it would be diastereomer. If it was RR to RS, if some chiral centers change, but some stay the same, that would be diastereomers, right? Because this is not a chiral molecule, we cannot say enantiomers here. So A is wrong. For B, we can say that it is a racemic mixture, which is a 1-to-1 ratio of enantiomers. Oh wait, no. wait. This is incorrect. This is incorrect statement. Incorrect statement. Oh, do you have the key for this practice exams? Then we could check our answer afterwards.
I do.
Okay. Let me check it afterwards.
The answer does include B.
Oh, the answer does include B?
Yeah.
Wait, hold on. Oh, okay. Oh, shoot. I'm getting ahead of myself. This is talking about H2 linear catalyst. It's not talking about sodium ammonia liquid. I was looking at the same thing here, right? So that's another thing when you take the exam. Make sure to read the answer choices and question problem carefully, so you don't overlook things and go too fast.
Yeah.
I thought B was also saying that we're gonna use sodium in ammonia liquid, but it changed it up on me. It's using H2 linearized catalyst, which would change up what our B is, right? We're now using H2 linearized catalyst, so our B is now here, right? And we said B is chiral, and because B is chiral, we can have a set of enantiomers, right?
Okay.
Making it a racemic mixture. So this one is good, but let's check with C. C would be a single achiral compound. Let's check C. C, which is going to be okay. That's when we react A with osmium tetroxide. A osmium tetroxide. Okay. I got so I was looking at the wrong thing for the last problem. If we use H2 linearized catalyst, that leads to this intermediate here, and then we react it with Br2, that would lead to this chiral molecule here, right? I was looking at the wrong chiral molecule. That's not the chiral molecule right there, right? But this is the chiral molecule that we're looking at, so that would still make sense. But if we look at C, after H2 linearized catalyst, which is this intermediate here, it reacts with osmium tetroxide, this is a meso molecule, making it achiral. Right? So C checks out. I mean, B checks out. Now let's go on to C. If we use sodium in ammonia liquid, then B will be a single achiral compound. So if we used this, B would be a single achiral compound. This right here is an achiral compound, so that checks out. That part makes sense. Now let's look at C. C would be a racemic mixture. Right? C would be a racemic mixture. So once we have this intermediate here, we use OSO4. C, osmium tetroxide, X, C would be a racemic mixture. Yeah. Then we would get this chiral molecule here, which is able to form a racemic mixture because we are able to have enantiomers. So that part of C makes sense. So we check that out. Now let's check D. If we use H2 linearized catalyst, which is this one right here, this is our intermediate. B, which is this right here, which is chiral, and would be a racemic mixture. This would not make sense, right? Because we end up with a chiral molecule, which will be able to form a 1-to-1 ratio of enantiomers, aka racemic mixture. It is not achiral, right? Because there's no plane symmetry. So this part of D does not make sense, right? So that would eliminate E, making the answer choice F. Right?
Got it.
Yeah. Okay. It. So Wiley, did you solve the
yeah. Yeah, I
problems
saw
that
that.
I sent you earlier? Okay.
Yeah. Let me try. Okay. First one,
Mm-hmm.
you just change the alcohol to a ketone
Yep.
because it's secondary.
Mm-hmm. Right.
Yeah.
You got it.
The second one, you turn the primary alcohol to a carboxylic acid.
Mm-hmm. Right. Primary alcohol into carboxylic acid using a strong oxidizing agent, Jones. Nice. And be careful here. A common mistake that students make is that they add or lose a carbon by accident. Right. Some students
Yeah.
draw the carboxylic acids like
I,
this.
I I remember doing that mistake when I was doing like predicting the products for like oxymercuration. Oh my gosh.
Oxymercuration, demercuration.
I got like a point lost, like off because of that.
Oh
I
yeah.
think I was trying to like make an aldehyde and I added or like removed a carbon.
Added, yeah, remove the carbon, right,
Yeah.
right. Keep track of the
Yeah.
carbon atoms.
Yeah.
Right. Okay.
Third one, the original is supposed to be the primary
Mm-hmm.
alcohol. Yeah, just an OH, yeah.
Right.
Fourth one, I put no reaction.
Mm-hmm. No reaction. That's right.
And then the reactant should be the primary alcohol on the cyclopentane.
On the cyclopentane,
Uh,
like this.
think?
Right. So what
Yeah,
kind of alcohol is this? Primary, secondary, or tertiary?
secondary.
Secondary, right. And if we use
Oh wait, oh I just removed the carbon, did I?
uh,
There should be a carbon like in
mhm.
place of the O,
Right, right.
and
So
then an alcohol attached to that. Oops.
right. Like this. Mm-hmm.
Yeah.
Yeah.
See, I keep making that mistake.
Adding or removing carbon. I know, I know.
Yeah.
Make it now so we avoid it in the exams.
Yeah. Oh, good.
Hmm. Yeah, it's good.
Oh,
Okay.
yeah.
So um let's go over reduction now, which is going backwards, like how we could reduce a carboxylic acid or aldehyde or ketone back into an alcohol, right? So I'm gonna start with ketone, then we'll move on to aldehyde, then we'll move on to carboxylic acids, right? So when we do this, we have to, I think this is on your final exam too, right, Nindini? Like the alcohol reactions, PCC, Jones.
I don't think I learned that.
Oh, not yet. Right, I see,
Is
I
this
see.
Orgo 2 or Orgo 1?
This is Orgo 1. It should be Orgo 1. Because I saw your practice exam, like it
They
had
have
like
like synthesis questions and stuff like that, but I haven't learned like PCC and
you,
Jones.
that's crazy. You gotta send me the textbook that you use later. I want to check it out because like the order that you, if you did not learn this and you learned aromaticity already and Diel's order, that without this, then that's pretty weird order. That's not the order I'm used to teaching or learning. Okay,
Right.
man. Right. So the reducing agents, there's going to be two of them. There's a weak one and a strong one, just like
Oxidizing.
the oxidizing agents. That's right.
Yeah, reducing.
So the weak one would be sodium borohydride, NaBH4. And then the strong one would be lithium aluminum hydride, LiAlH4. Right.
Oh,
We
okay.
tend to see this happen in acidic conditions afterwards, like acid workup. Right. This tends to be the first step, and we tend to see a second step of acid workup, like H3O plus. And then I'll show you why in the mechanism, well, like the intermediate of the mechanism. Right. If we have a ketone, it does not matter what you use as a reducing agent. You could use the weak or strong one, NaBH4 or LiAlH4. Second one is going to be H3O plus. Second step.
Okay.
When you see a reducing agent, this is what I want you to think about. I want you to think about a hydride ion, a hydrogen with a negative charge.
Yeah.
That H minus right there, what do you think it could attack from that molecule right there? Think about the polarity here and differences in electronegativity. Like if, would this be the nucleophile or electrophile?
It
The
should be the
hydride.
nucleophile.
Nucleophile, right. So if that's a nucleophile, which atom here would be electrophilic? Which one would be the
Oh, that'd be
electrophile?
the carbon attached to the double
Yeah.
bond oxygen.
Yeah, that carbon directed to the double bond oxygen is the electrophile. So this H minus here is going to attack that carbon attached to the carbonyl carbon. But that's going to break the octet rule because we're trying to make a bond between
Yeah.
this carbon and hydrogen. So do you know how we can conserve the octet rule?
You move the double bond from the O to the double bond to the O.
Yeah, we pop the double bond into the oxygen, where one bond here represents 2 electrons. So we're basically moving 2 electrons to that oxygen. When we do that, we're going to have this oxygen with a negative charge because it gains a pair of electrons, right? Before it only had 2 pairs of electrons, but now it has 3 pairs of electrons. It gains a pair of electrons from that bond right there, popping onto that oxygen.
Yeah.
And the hydrogen is now attached to that carbon that it attacked. So this carbon still maintains its octet row. Now that's the product after the first step. That's why we bring in the acid workup step afterwards, after the second, like in the second step, right? That acid workup step is just going to neutralize or clean up the product by protonating the O minus to make it to neutral OH, like that. So that's why we are reducing this ketone into that alcohol using this reducing agent, right?
Oh, okay. Wait, let me
Sodium
draw.
borohydride or lithium aluminum hydride. But we tend to do an acid workup step to follow up to clean up the alkoxide ion, the O minus.
Yeah.
This is an alkoxide ion. Right. Okay. So same for aldehyde. Does not matter what you use. You could use a weak reducing agent, sodium borohydride, or strong reducing agent, lithium aluminum hydride, with the second step of acid workup. Now, let's have you walk through this mechanism for me. What would happen here?
The hydride ion would come in to attack the electrophilic carbon.
That's right. And
And
if you want me to be more like accurate in this mechanism, I just want you to think about the hydride ion as the thing that is attacking the carbon, which it is, but it will not be floating by itself. The hydride ion is coming from, let's say if we use sodium borohydride, this is what it would look like. Sodium is positively charged. That means
yeah,
the boron is negatively charged. Because this boron is negatively charged with 4 bonds, like it's one of those weird atoms in the third column that has a negative
yeah.
with 4 bonds. All of these hydrogens are very angry, and they will act as a nucleophile, as a hydride ion, which would attack that carbonyl carbon
Okay.
there. Right. So that's the more accurate representation of the mechanism. I just wanted to simplify it at first, but this is what it would actually look like in the mechanism.
Okay.
Right. Okay. What other arrow am I missing here?
The double bond to the O
Yeah.
for the electron pair.
Right. Okay. Negative charge on that O. Now, second step, acid workup.
Yeah, the negative charge on O would grab one of the hydrogens, and that bond from hydrogen to oxygen would get to the oxygen to balance the charge.
That's right. That's right. Giving us this primary alcohol and this inorganic water here. But that's a side product. The organic major product is that alcohol, right? Where we reduce this aldehyde, carbonyl-carbon, into a primary alcohol right there.
Oh, okay. Wait, so it's literally just the same mech. It's just that you get alcohol on a different.
Right. Same
Okay.
mechanism as the last case, but instead of this R group here, we have a hydrogen.
Okay.
Right. So instead of that R group there, we have a hydrogen like that. Right. Okay. Now for carboxylic acid, this one here, it would matter what you use, right? If you used a weak reducing agent, sodium borohydride, second step acid workup, that is not strong enough to reduce the carboxylic acid, no reaction.
NaBH. Okay.
Right. But if you use a stronger reducing agent like lithium aluminum hydride, LiAlH4, and second step H3O+, that would be strong enough to reduce the carboxylic acid into the primary alcohol. Think of it as cleaving off that carbonyl right there. Right. And the mechanism here, I don't think you need to worry about for Beal. I want you to send me his lecture notes just in case that I can go over this with you. But I can explain to you why the weak reducing agent here does not reduce this carboxylic acid. Right. What do you notice that this carboxylic acid can do that the ketone and aldehyde cannot do to make it more, that makes it more stable?
Resonance.
Yeah, resonance.
Delocalization. Sorry,
yes. The resonance or delocalization is able to occur here. Delocalizing the electrons, having more resonance structures, making it more stable, which makes it less reactive. Right?
Oh, okay, that makes sense.
Unreactive.
Yeah.
Right. So that's why an unreactive reagent would not be reacting with an unreactive molecule.
Yeah.
Um,
so could you technically just put like LA8 LiH4 for like all of them?
Yeah, for synthesis you can put it for all of them, but for predicted products, he might use
no reaction
that, and you would just put no reaction like that.
Yeah. Okay.
Yeah. Now let me give you some practice problems, and then I'll go over another problem with Nandini, and then we'll end up the session by checking your answers.
I'll leave the bathroom quick.
Okay.
I'm back. Are these just two problems?
I'm gonna give you one or two more.
Oh, okay.
Yeah, I'll give you one more, so 4 in total. So these are the 4 that I want you to answer here.
Okay.
Do you have a screenshot or these written down? Okay. Okay. To the next one.
Oh wait, can you go back?
Oh yeah.
I forgot to screenshot it. Oops.
Yeah, that's okay. That's okay.
Okay. Now you're good. Now you can.
Yeah.
Thank you.
Yeah. Ooh, H&MR. How do you feel about H&MR, Nandini?
Not good.
Not good. I know that was my.
I don't even remember half of this stuff. I started studying like last week.
Last week?
Yeah.
Oh my gosh. Like, is it like most of the material that you don't remember of this?
No. I do know most of the material. It's just like
Uh-huh.
H&MR, CNMR.
Oh yeah. I didn't see any CNMR, IR, or mass spec
Oh,
problems.
because this is exam 3, the one that you're looking at right now, and then I sent you post exam 3, which is basically like all of like the rest of the material that was covered after Thanksgiving. But I also have exam 1 and exam 2. They like sent out like a comprehensive like packet.
Right, and that would be included in the final, right? Like the exam 1, exam 2.
Yeah, because the final was cumulative.
Yeah, can you send me that one too? So then, like, if you like come back to the future office hours, I could like look through those files for the IR, CNMR, mass spec as well.
Cool.
Yeah. Okay. So HNMR. What type of signal is expected in the HNMR spectrum for the indicated hydrogen atoms? Okay. So there's different factors for HNMR. There's integration. There's coupling, aka the n+1 rule, or neighbors, how many neighbors a set of hydrogens have. There's de-shielded versus shielded. Range. There, aka I say this downfield or upfield? Downfield. I think this was downfield. Downfield, yeah, downfield. But the more common term is to use like de-shielded versus shielded. This is upfield, I think. Okay. But this question here is specifically asking for if you remember, what would you guess? Integration, coupling, or the de-shielded versus shielded range? It's okay if you don't remember, but if you were to guess,
if I were to guess, probably coupling.
Yep, coupling. That's right. Which is the number of neighbors. These are the indicated hydrogens here that they listed out. Do you remember how we can calculate the number of neighbors those set of hydrogens have?
N+1? No.
Yep.
Is that
Okay.
okay?
N+1. Oh, that's gonna show up on the HNMR, right? Like how many subpeaks that set
the
of
peaks. Okay, okay.
the subpeaks those hydrogens would have. But how would you determine the neighbors like of these hydrogens? To do that, start at one of the hydrogens of the set, right? This is the set right here. The set has two hydrogens.
Okay.
And then go 3 bonds away. This is 1, 2, and then 3 is a hydrogen right here, right? Okay. So I'm going to draw the neighboring hydrogens in pink, right? So this is considered one neighboring hydrogen because it's 3 bonds away from the hydrogen we are interested in. 1, 2, 3, like that, right? If we go like this, 1, 2, 3, this is not a hydrogen. That's a carbon. That does not count as a neighbor.
Got it.
Right. But we could go the other way. We could go 1, 2, and then 3, like that. Right. Okay. So that is another neighboring hydrogen right there. So this set of hydrogens here would have 2 neighbors. So the n here is 2. This question here is asking for what type of signal or how many subpeaks would this set of hydrogens have. That's when we use the n+1 rule, which is going to be 3, right? A triplet. And that's going to look like this, right? Where this is one overall peak representing these 2 hydrogens, right? These 2 hydrogens here, that 2H, that's the integration. How many hydrogens are in that peak? But the subpeaks that you see in that one peak is the coupling, the n+1 rule, right? This does not show the exact number of neighbors you have. It shows how many neighbors you have plus 1, right? So at the HNMR, if you try to read off of a graph and you try to determine how many neighbors this peak has, the neighbors would be equal to the subpeaks you see minus 1, right? In this case, we see 3 subpeaks, minus 1, 2 neighbors, like that. But that's going reverse. Like that's for a different type of problem when we try to predict what a molecule would look like based on the HNMR they give us. But in this case, they're just asking us what would the peak look like. It would look like a triplet with 3 subpeaks like that.
Okay.
Right. I want you to like do, let's say, this hydrogen here. So I'm going to use the same exact molecule that they gave us. Right. And I'm going to list out the hydrogen that I'm interested in, and I want you to determine what type of signal is expected for this hydrogen here.
So wait, for the answer for number 16, you got triplet?
Triplet, let's see. 1, 2. 1, 2, 2 plus 1 is 3. Yes, is the answer something else?
Yeah, it's doublet of doublets.
Doublet of doublets.
Yeah, it's E.
Doublet of doublets. Let's see. See, what type of signal is expected in the HNMR spectrum of limited hydrogen atoms? So let me try to think about this doublet of doublets. So these are the hydrogens. These are the neighbors. Of doublets. Of triplets. Huh. Let's see. Two inducing percentage splits this into a doublet. Each line of this doublet is then split into a doublet. Oh, that's interesting. Okay. I'll look more into this problem, and then I'll get back to you on this problem next office hours.
Okay.
Not too sure this one. Yeah. Let's see. Because when I took OChem, my weakest area was always the spectroscopy. Like it was always the HNMR, CNMR problems. But I'll get back to you on this this problem here for next office hours.
All right.
Let's see. Yeah, it's more spectroscopy problems. Okay, yeah. So let's end off the session by checking Wiley's answers if he has them.
Okay. Yeah, I have.
Yeah.
Sorry, it's not opening. There we go. For the product, it's just you take the ketone and make it a primary or secondary alcohol.
That's correct.
For the second one, you can either the thing attached to the benzene ring could either be an aldehyde or a carboxylic acid.
Right. It could either be an aldehyde or carboxylic acid, because when we use a strong oxidizing agent, it could reduce both an aldehyde or a carboxylic acid. That's right.
Third one, it should just be a secondary alcohol in place of the aldehyde.
Secondary alcohol, like this.
Yeah. Oh no. No, it's just the alcohols attached to the. I don't know how to describe it.
Like to this carbon here.
Yeah.
Right, and this would be a primary alcohol.
Right? Oh yeah.
Because that carbon there is attached to one other carbon like that. Right.
Yeah.
Nice.
And there's no reaction for.
Yeah. Because carboxylic acid cannot be reduced with a weak reducing agent, NaBH4. Nice, you got it. Okay. Yes. So that is the oxidation and reduction of alcohols, Wiley. Tomorrow we'll go over the organometallic and Grignard reagents, like the RME or RLIs. And then tomorrow, Nandini, if you show for office hours, we'll go over this spectroscopy problem and more in depth about spectroscopy, like HNMR, IR, CNMR, all those things.
Okay. All right.
Yeah.
Thank you.
No problem. See you guys. Good night.
Yeah, see ya.
Bye.
Bye. Good night.
Good night.